Today I want to talk to you guys about signals. Now a few weeks ago on the channel I released a video talking about SBUS and we took a deep dive into it. I showed you how it looks on an oscilloscope. I showed you how the differences are between the inverted and non-inverted, whether it be FR Sky or Futaba. Now today I want to take a look at some other signals that you will find on an autopilot or a drone. Specifically we're going to take a look at the UART connection and we're going to take a look at I2C as well. I will also show you guys a little bit about SBUS too if you haven't seen that other video, but if you do want more info on SBUS, I would strongly suggest taking a look because I do a bit of a deep dive into how the whole serial receiver system actually works. Now we're going to be using the oscilloscope today, which is the Rigol, and we're going to be showing you this on the V5 Plus from CUAV on this F450. Now it doesn't matter what autopilot you are using, what software you are using, the basics to these tests are all the same, and what we're actually looking at is the raw signal data on the oscilloscope rather than actually interpreting what it is, whether it be Mavlink or MSP or anything like that. Now, as I said, we're going to take a look at it on the oscilloscope and it's going to allow us to look at the signal in a different way compared to what you would do on a multimeter. And whilst you don't need an oscilloscope for every kind of diagnostic, it is a very handy tool to have on the bench and it does allow you to take your testing to the next level. Now, today's video would not have been possible without the support of Telonic Instruments in the UK. They have very kindly sent this over to me to look at, and I would not have been able to make these videos without their support. Now, Telonic offer sales, rental and repair of a vast range of test equipment, including oscilloscopes, multimeters, spectrum analyzers and power supplies. They have been supporting the electronics, education and manufacturing industries in the UK for over 50 years. Telonic have a massive amount of experience in the testing industry and stock a wide range of models from Rigol, Siglent, Delta Electronica, among others. And whether you're a hobby user, in education or business, they have a range of models to suit your budget in stock for fast delivery. For more information on how Telonic can help you with your testing needs, you can find them at www.telonic.co.uk, or you can also check them out in the link in the description of this video. Okay, so what we're going to do is take a look at this F450, which has a CUAV Vision 5 Plus autopilot on board with Ardra installed, and we're going to look at a couple of the signals on the oscilloscope that you get from the controller. Now, if you've seen my other video, I actually did a deep dive into SBUS controls specifically, and I'm not going to really touch on that in this video, but you do want to have a look at that if you are interested in seeing what the RC signals look like on both SBUS as well as traditional servo signals as well, and I'll put a link to that video in the description of this one. Now what we're going to look at today is basically three different signals. We're going to look at the TELEM2 output, which is going to the DJI digital FPV air unit. We're going to take a look at the I2C signal, which is coming from the onboard compass into the autopilot, and we'll also take a look at the GPS signal that is going into the autopilot as well. Now, just to show you how I've got this set up, I've added an extra cable into the TELEM1 port, and this is simply going to be my ground reference for the oscilloscope, and I'm just going to clip my main ground connection on my main probe onto that wire there. So rather than have to actually clip in all over the place on the air unit, that one is just clipped on and it's ready to rock and roll. Now I've got the scope set on ×10, which is what you should really have it on for something like this, and I've also then got it set up on auto trigger, and I'll take you through that as we're looking at it anyway. So the first signal we're going to take a look at is the TELEM2, which is the MSP signal or Mavlink, depending on what setup you're using, which is going to the air unit. Okay, so let's take a look at the first signal we're getting, which is on the TELEM2 port, which is coming from the DJI air unit. Now this is a UART connection on MSP, and it is an asynchronous signal, which means there is no clock line. There is simply a TX from the autopilot through to the air unit and an RX from the air unit back to the autopilot, and then the data stream is simply clocked by it measuring a start bit and end bit and then trying to calculate the data in between it. There is no clock signal included with it to tell it what bits to read. As I said, it is simply an asynchronous signal. So what we're going to do is go on to the TX pin. First of all, I'm going to hit auto on the scope and let that then actually begin to do a reading on it, and then you can see the signal data appear on the screen. Now this is a live digital signal, so that is why you are getting the movement showing on the screen. Whilst the trigger is correctly set, and it is set to actually freeze frame, which it's doing, the reason you're getting the data flicker is because the signal is actually changing. It is not a static signal, it is a live signal of data that is coming through into the scope. And if we actually zoom right out, you can see the individual bytes of data moving through as the data is being transmitted from the air unit to the autopilot, or from the autopilot to the air unit. Now, the first thing you may notice is that this is an inverted signal. It sits at plus 3.3 volts at the top, and then it is dragged to ground to represent a 1 on the digital data scale. Now, if we wanted to take a look at one of these packets of data a bit closer, we would simply hit single. We've then freeze framed one of those screenshots on the screen, and then we can actually zoom in and take a look at the data that is contained within that snapshot that we've just taken. And you can simply see the noughts and ones of the data stream being represented as the signal goes up and down. Now, it's easy to see that it's inverted because if you look, the signal starts at a high level. We've got it measured at 3.48 volt. It's basically 3.3 volt signal. And then as we scroll along on the scope, you can see the individual noughts and ones showing on the display as the data stream is coming in. Now, we are not decoding this. We are simply looking at the raw data itself just to see how the signal looks. And from a diagnostic point of view, if we were looking to actually see if there was a problem with this bus, this is enough information to do that. We can look at how the signal actually looks. Is there any strange interference? Is there any strange shapes on the clock signals themselves? So is there any like drop-offs that shouldn't be there, or any final issues on the end of the wave where it starts dragging itself down and things like that? We can see that we've got all nice square waves, so we are happy that that signal is correct. And then we can hit run and actually see the whole signal coming through as the data is happening. Now, if I switch over to the other line, which is simply, one of them is TX, one of them is RX, again, you can see the data stream coming in and the data is continuously moving through the screen. So again, if I zoom it right out, you can see the data is just continuously being refreshed as it's coming into the scope. And again, if we wanted to take a closer look, we would simply click on a single capture and then zoom into that, and again, take a look, have a look how the signal is actually looking, look at the noise level that is sitting on the signal. And we could even actually jump right in, and if we really wanted to, is measure things like the amount of extra voltage that is along the top, and if there's any noise and things like that. But here and now, that signal looks absolutely fine. And for the UART, it looks absolutely spot on, so there's nothing there to be concerned about. Okay, so next we're going to take a look at the I2C bus, which takes the mag data from your compass to the autopilot. Now, unlike the UART, which was a TX and RX line, which was asynchronous, this is a line which has a clock signal and a data signal. And rather than one device transmit on TX and one device transmit on RX, everything transmits on the data line, and it uses the clock pulses to know when it's able to transmit its data and how to actually read that data as well. So to be able to look at this on the scope, we actually need to use two probes. We need to measure both the clock signal as well as the data line as well. So what I'm going to do is hop on to both connections on the autopilot. And as you can see, the signal has now kicked in. Now on the yellow channel 1, that is the data signal, and the blue on channel 2 is the clock line. And as you can see, it is only transmitting the data alongside the clock signal itself. So if I was to actually zoom right out, you can see that the data at the top is only transmitted at the point where there is a valid clock signal. Now, when we actually zoom into this and take a look at it a little bit closer, and if we actually take it as a freeze frame, you can see each pulse of the clock located along the bottom, and then the position of the data line at the top is used to represent a 0 or a 1. So every time there is a pulse, the microprocessor will look at what the position of the data line is. And that is how I2C actually works. Now again, we are simply looking at just the clock line here, and we're not actually decoding, but we are able to take a look at it and actually see how it looks. Now what is quite interesting is if we move along to the middle there, you can actually see that there's a bit of a double pulse at that point, which is virtually it's about just into the line, and it's not quite a full pulse. If you look at it, it's actually a staggered, it's a full size pulse, and then it extends back out again, and you can see the blip for it on the top one as well. Now I'm not too sure what that is exactly on the data line, but it is actually repeatable as well when you actually run it all of the time. And if I zoom out to that one, and if I say take a snapshot of all of them and zoom in, we can see it's on that one. But if we move the line across, zoom in on this one, you can see that it is there as well. And we've got that double hit right in the same place as well. So it's certainly some form of marker on the data signal too. But that is how I2C works, and that is the position data showing along there for the mag along the top, and then the clock line running along the bottom. Now if we were running multiple devices on this bus, you would see multiple instances of the clocks and multiple instances of the data as well. The reality is at the moment on this I2C bus we only have the compass, so there is only one set of data being transmitted, but it is easy to see it. And again, just like the UART, it is an inverted signal which starts in the position of high and is being dragged to low to represent a 1 on the digital data scale. Now one more thing I'm going to show you on the I2C is that we can actually decode some of the data on screen. And whilst first of all on both the UART and the I2C we were simply looking at the waveforms, the scope has a built-in decoder for I2C, and we can actually take a little bit of a look at the data itself. So I've gone onto the math function and I'm going to turn decode on, and the scope is now going to start decoding the data that it is seeing on the screen. So what I'm going to do is hit stop so the data actually freezes, and then you can see the information showing along the bottom. Now the easiest way for me to do this as a full capture is I'm going to zoom out a second just to get the full waveform, hit stop, zoom in a little bit closer, and then we can see that it begins to decode the data. Now if I scroll down we can have a look. At the moment we've got it in hex. We can change it to binary if we wanted it in binary as well. We can change it to ASC or that, but I'll keep it in hex for the purpose of this. But as you can see, what we've got is the data. We've got W0E, we've got 03, ROE, 1B, 00, and then if I scroll along, you can see the rest of the data will actually begin to decode. Now, I'm not going to fully decode it in this. I'm not going to get into it in any great depth and actually have a look at what that information is actually saying. However, we can take a look at it on the scope, and you can see that it is showing along the bottom. And as we scroll along a little bit more, it's lost the decode. There it goes. It starts again then. And the data is continuing to be decoded as we move along. And if I wanted to, I could switch it over to binary, and then you can see the actual binary value for each individual bit. And the interesting thing is when you look at it in binary, if you actually move in and then move across, you can then see where the zeros and the ones are. So if you actually look, you can see that it is 4 zeros, 1 0 1 0, so that's 1 0 1 0, and that is the actual digital data being decoded on the screen as each individual clock pulse is coming through. So that is the nice thing that you can actually do with I2C as well. And again, I'm going to pop him back onto hex. But if you wanted to, then you could actually take this data, go onto the chart, decode it, and then actually have a closer look at what actual information is being transmitted on the bus if we actually wanted to do it as well. However, here and now, it's simply an easy way to have a look at what the I2C is saying. And again, from a diagnostic point of view, we simply really need to see that the signal looks correct, but we could go into a lot more depth if we did want to decode it. The next signal we're going to quickly take a look at is the GPS signal from the unit, which is again simply a UART connection. It's an asynchronous signal, and we're going to simply hop onto the white wire, which is our TX from the GPS. And as you can see, it's appeared on the display, and we're now getting the GPS data signal coming from the GPS down into the scope. And if we again just zoom in, you can see that the data is actually changing because it's live data from the GPS as it's actually coming in. Now, if we wanted, again, to look at it in a little bit more close detail, we would simply hit stop, and we can then zoom in on the data once again and have a look at it in action and just see how it looks. And again, it's identical to what we had from the UART connection. It's an asynchronous signal, which means there is no clock signal. It is inverted, which means it is pulling from positive to ground, and it is as simple as that. So if we did want to make sure that was working correctly on the scope, we could simply put it on run, zoom out, and we get the signal there, nice and easy for us to be able to see and check on it and make sure that it is working correctly. Okay, the last bit of data I'm going to show you is the SBUS signal quickly. Now, I have done a dedicated video on SBUS where I take a deep dive into the signal, talk about it, tell you the different types and how it all works. I would strongly suggest checking that out if you do want to know more information on SBUS, and I will put a link to that in the description of this video. However, what we'll also do is take a quick dive onto this one, which is coming from my DJI Air unit, and you can see that it has now appeared on the screen on the scope. Now, this signal is the SBUS, and it is inverted SBUS, which means ground represents 0 and 1 represents plus 3.3 volts. Now, you will notice that that is opposite compared to the UARTs that I was showing you earlier, and I was calling that inverted. And the reason is inverted SBUS is inverted compared to Futaba, and I explained the whole thing in that other video, but the reality is this is inverted SBUS. Now, if we take a zoom into the signal, you can actually see the individual bits of digital data showing on the screen. Now, the cool thing about SBUS is you can actually see your RC signal change the data that you're displaying on the screen. So if I begin to move my stick around, you can see the noughts and ones in the digital data stream move around. You can see that they're actually changing. If I stop, the data pretty much freezes. There'll always be some slight changes as the packets of data are coming through. However, if I move my sticks, you can see that's moving the throttle up and down and yaw. You can see that the data is moving, and then if I stop, it all goes static. And then if I move the right stick, you can see again the noughts and ones in the data stream are moving around, which means that the data is changing. And then when I stop, it all goes static again. So it's again nice and easy to be able to actually, test the RC signal looking at it on the scope. And whilst this isn't perfect, it's certainly not going to go, oh, it's working absolutely 100% correct. We are able to take a look at how it looks. And if I actually scroll along, it's actually quite hard to do this kind of signal that wants to keep moving. Trying to just move him along a bit without it. And then if I go to there, and again, you can see if I do that on, if I change a switch, you can see changing the mode switch, the data on this end of the signal actually changes. And you can actually see the individual package change within the data stream. So that is SBUS. And again, as I said, if you want to deep dive into it, please do check out my other video. And that is pretty much all of the signals on the autopilot. Now, an oscilloscope is very handy for doing diagnostics on equipment, and whilst it isn't the perfect tool, it does mean that you're able to visualize those signals on the screen, so you can hop onto your UARTs and have a look at how the signal looks. And if you are having problems with interference or the signal dropping out, you will actually see things like that on the scope screen. You can look at how much noise is on the data stream as well, what the voltages are like, and just get into some more complex diagnostics that you can't do with something like a multimeter. And it is good to be able to hop into it and again interact with that signal as well, just like we can with the SBUS, and move the data around and see that data being changed on the display as we are putting an input. And it's just something you cannot do on a multimeter, and this oscilloscope does help you diagnose your electronic issues a lot easier and quicker. And especially if you're trying to find things like data lines, it's very quick and easy with a scope to be able to pin around in a connection and go, right, okay, what does this one here do? Oh, that's plus voltage, and we can see that's plus 5.36 volt. Move across to the next one, No, that one doesn't really do anything. Move across to the next one and go, ooh, we're getting some data on that one. Move across to the next one and go, oh, there's a data line. And then you can actually pin connectors out. And again, if you want to get into more advanced things like hacking and things like that, you're able to actually get in there and take a look at the signals and then actually have a look at what the port's doing and maybe hook it up onto a computer and then start having a poke around. And that is pretty much it for this video. Now that is pretty much it. Now I'm going to keep making videos like this in the next couple of weeks. We're going to keep looking at signals on the drones. We're going to look at some of the ESC signals. We're going to dive into I2C in a bit more detail in another video as well. And we're going to keep looking at the scope and how we can use this to actually look at signals on a drone and an autopilot, as well as look at other things with the scope as well. Now, this video would not have been possible without the support of Telonic Instruments in the UK. They very kindly, as I said, sent this over to us to look at. And if you are interested in getting yourself an oscilloscope, any test equipment, please do check them out. There is a link to them in the description of this video as well. If you'd like to support the channel, please do consider hitting that subscribe button and also hit the little bell next to it as well, so you will receive updates on any of those new videos when I do release them. There's also a PayPal link if you'd like to donate to the channel, whether it be to support us or buy us a coffee as well, to be able to keep making videos like this too. That's it for this one. Thank you very much for watching. As I said, please do hit that subscribe button and I will release another video again in the future.